Okay, so let me continue with presenting our experts today. And let me introduce and welcome Professor Leo Wanner. Professor Leo Wanner is the research professor at the Catalan Institute of Advanced Research and Studies, currently at the Barcelona Supercomputing Center. And Professor Wanner earned his diploma in computer science from the University of Karlsruhe and his PhD in computational linguistics from the University of Saarland, Germany. Before joining the Catalan Institute for Advanced Research and Studies, he held different positions at the German National Center for Computer Science and different universities, such as University of Waterloo, University of Stuttgart, Pompeu Fabra. Also, he was a visiting researcher in numerous international universities, such as University of Montreal, University of Sydney, Southern California, Paris 7, Columbia University, and finally, University of Augsburg. Throughout his career, Professor Wanner was involved as a principal investigator in national and European research projects. He published 10 volumes and over 230 peer-reviewed articles. He's the associate editor of the Computational Intelligence and Frontiers in AI, and he is a regular reviewer for a number of high-profile conferences and journals in the field. His research interests include computational lexicology, deep neural language analysis and generation, abusive language detection, and conversational agents. So thank you, Professor Wanner, for being with us today.
And our last expert is François Lareau. I don't know if I went.
Yeah, perfect.
He's associate professor at the University of Montreal, and Professor Lareau has a joint PhD in linguistics from the University of Montreal and the University of Paris. He has worked as a researcher at the University of Subirats, University, Macquarie University, before becoming a professor at the University of Montreal in 2013.
Well, thank you very much for inviting me. It's a pleasure to be here at this university. Well, perhaps we would be all agree, or almost all, that cognitive semantics has had a great impact in the development of linguistics. And probably this is due to two facts. First of all, the rejection of traditional reference semantics, the idea that reference can explain meaning in a way. With this rejection, cognitive linguistics had to develop a new model of meaning, and this model was structured with scenarios that we call semantic frames. So not only did they rejected the traditional referential semantic theory, but they proposed a model that allowed us to develop and explain meaning as a construction, not as reference. What is frame semantics? You probably all know it, but just to make sure that we are all talking about the same thing, I will explain what a frame is. A frame is a cognitive structure, and it's a kind of cognitive structure that allows us to try to build an explanation to how we construct meaning. Basically, a frame is a schematic representation of a scenario or a situation, or I would say a micro situation, which is evoked by lexical units. And the frame is this scenario which involves various participants and props, implying objects, instruments within this scenario, and perhaps other conceptual elements. This is the idea of frame that was proposed in 1985 by Fillmore, and I think it's still useful, and we will see how, in what ways we apply frame semantics to the study of lexicon. I had, sorry, I wanted to have a slide to explain it because it might be. Lo he puesto aquí antes. Está en el. Es untitled.
Could you give us the pen drive again?
Well,
Okay.
lo bajas al tercero, al cuarto.
¿Tercero? ¿Este no?
No, no, tercero, cuarto. Okay. Well, sorry for the interruption. No, el cuarto, sí. So the idea is that we establish a relationship between frames and constructions. Frames are in the upper part of the slide. The constructions are in the lower part of this slide. Okay, and we put them all together because in our presentation, in our way of understanding meaning in language, we have both together. We don't consider as generativists, for instance, that semantics is a derivation of syntax, neither that syntax is a derivation of semantics. We consider that they are both related and that we cannot break this union between one and the other. And this would be an example of a frame, okay? Request is this frame. A frame has 3 core frame elements, and there is a specific relationship between these frame elements. In this case, a speaker sends a message to an addressee, and this frame is evoked by the verb to ask in Spanish, pedir, because it is Spanish framenet. So it evokes, it calls, if you want, this frame, but at the same time, the frame returns all this structure, which is the syntax related, and what we actually are interested in is not only studying the frames, but study also the semantic expression, or if you want, the semantic or syntactic expression of these frame elements in a specific phrase sentence like this one, okay? So actually in FrameNet we have these 3 parts. We have frames, we have semantic expressions and syntactic expressions, of these frames, and we annotate the frame elements of the sentence and we add information about their syntactic phrase type and grammatical function. For instance, here we have noun phrase, external argument, etc. Okay? Well, we don't have too much time, so. Of course, we not only study verbs, we consider all kinds of predicates, like here in this example. I don't know if I should be in this situation, you see. In this case, solicitud is a noun, request in English, and in this case, we have the same situation. So we are actually studying verb, nouns, adjectives, and other elements, provided that they are predicative elements. And, well, this has provoked a group of projects which are now a consortium, which is called Multilingual FrameNet. And Multilingual FrameNet is a consortium of monolingual FrameNets. The most historically, chronologically speaking, was English was the first FrameNet, the second was Spanish, then no, I don't need.
Ah, okay. Thank you.
No, that's all I need. And the activities that we develop in this FrameNet semantic analysis involves, as I told you before, identifying the semantic frames that were here evoked by lexical units referring, of course, to word senses, analyzing how frame elements are expressed in grammatical constructions, okay? So these two levels of expression. But of course, this is what we have been doing. Actually, FrameNet is going on, is continuing in English and in many other languages. But if we want to keep these projects going, and if we want to continue our job, we have to be interested, firstly, in artificial intelligence, because artificial intelligence will be absolutely necessary to continue these projects in the future. for a very simple reason, because developing a FrameNet means a lot of work, and we can automatize partly this part of these tasks if we use artificial intelligence in a way which suits our needs. So, as you all know, the rise of generative artificial intelligence has impacted linguistics and many other. I think it has impacted the whole world. So this is not an issue, but especially for us because it has advanced the natural language applications in a spectacular way, so that natural language applications based on artificial intelligence outperform the traditional or the previous methods that we were using in linguistics. And one of the points that I wanted to talk about today, which is this second part of my intervention, is the fact that not only artificial intelligence not only outperforms all existing previous systems, but outperforms them without using any explicit linguistic theories. That's really a problem that we should explain, and perhaps we can debate today how any of us, but what are our opinions of this fact, which is, I think, quite surprising. May I? As you all know, probably, but let me mention once more, language models are trained on massive corpora of internet text, as you know. Massive meaning today, we don't know next week or in 2 weeks, but hundreds of billions of words. And they are trained by learning statistical patterns of language use, basically by transforming word contexts into probabilistic occurrence values. This is really surprising, at least for the people that have been working and following the whole history of these computational developments in linguistics, that the core of artificial intelligence is based on probabilistic contextual values. Okay? So, as we said before, language models are computational architectures that during training process text segments, strings of words, map them into embeddings, which are multidimensional vectors encoding probabilities, probabilistic co-occurrences patterns, which refer to word likelihoods, which is the same as I was saying before, just a little bit more technical. The only thing which is important for language models is distribution. And that's the information that they use afterwards to generate text across diverse NLP. Embeddings, then, and language models, but because embeddings are in language models, constitute probabilistic representations of distributional and combinatorial properties of words within text sequences. That's all we have. And that's how it works and how it surprises for their efficiency, especially in natural language applications. Consequently, the distributional analysis is the foundational core of the linguistic knowledge of language models. The idea is that words that appear in similar contexts tend to have similar meanings. And conversely, the difference in meaning between words is directly proportional to the differences in their linguistic contexts. Okay? So, to look at it from a different perspective, more general, we could say that language models model semantic similarity and difference through contextual co-occurrence patterns, which is the same as saying that similarity and difference is a byproduct of context windows. Of course, probabilistic context windows. But let me insist again that this force-meaning relationship that is used by language models doesn't constitute a full theory, at most a part of a linguistic theory, not even in the theories of Harris, which was the founder of the idea of distribution in linguistics, one of the people, the linguist that spoke first about it. He didn't propose it as a theory, as a general theory, but as a particularity of languages, as an aspect that could be studied and that had been studied before, hadn't been studied deep enough before. So it's important to know that the core, even if the language models use form-meaning relationships internally in its system, this form-meaning relationships, even if it puts forms and meanings together in a way, is not a linguistic theory, okay? And the question which I wanted to propose and discuss, perhaps, if you find it interesting enough, is how has generative artificial intelligence achieved such high cumulative effectiveness despite lacking any adherence or following, maybe without following any specific linguistic theory? I think this is one of the main points that we should think about, perhaps, if you, or in another way, by what mechanisms does generative artificial intelligence attain human-like communicative competence without any explicit linguistic theoretical grounding, or any is perhaps too strong, with explicit linguistic theoretical grounding, because we said distribution is at least a linguistic criteria to to develop the applications in natural language processing. And here is one of the possible answers to the previous questions. I still have a second question that has no clear answer, but at least this one does have an answer. And the answer would be perhaps that general artificial intelligence are based on continuous probabilistic computation, and as such, they can adapt better, far better, than deterministic rules-based systems. Okay? So it's not by chance that they get these levels of precision. It's because a probabilistic system is better adapted to the analysis of a system like language, which is which has a prototype structure. So probabilistic systems are more adapted to the multiplicity of factors that shape the prototypical structure of human languages. Okay? And this is a point of view that has been pointed out also by Piantadosi in 2023 in a paper which I strongly recommend to you. It's online and it's fantastic. Perhaps because he's not a linguist, and not being a linguist, no, I mean, I have nothing against linguists. But perhaps because he's not a linguist, he can be tougher with linguistics than we can be, of course. But he's a psychologist, he's a professor at Berkeley University, and I think it's really one of the best papers, the most enlightening papers I've been able to read about this subject. Until, of course, 2023. There are many others. There are papers coming out every day. And now a question that we can't answer definitively, which is even more interesting, even more and more basic than the previous one. How is it possible that a principle as basic as the distributional form-meaning relationship, hardly, as we said before, a complete linguistic theory, so distributional form-meaning relationship is not a linguistic theory, and how is it possible that they can be so effective, that this relationship, distributional relationships can be so effective for artificial intelligence systems? The core paradox is that distributional semantics reduces meaning to words in context, a radically minimalist premise, yet this alone powers language models to near human fluency, bypassing decades of complex linguistic theorizing. And as I said before, there is no definite answer, but I think there can be a proposed, I will talk about a proposed solution to this, answer to this question that seems quite plausible, and I think it opens a line of research for linguistics and computer scientists together to understand better certain aspects of communication and certain aspects of what artificial intelligence can contribute to other aspects of linguistics, like neuroscience and neurocognitive linguistics. Un minuto. I am at the end. 1 minute. Yeah, I have 1 minute. And he proposes in this 1 minute, I have enough time, that distributional learning, distributional unsupervised learning, induces latent grammatical structures in language models. Okay? So it's that the same process, even if we don't do anything, that language models, they create latent grammatical structures. So it's like saying that language models, even if we don't do anything because of their the billions of data they create in the embeddings, etc., all this structure creates latent grammatical structures that allow these extraordinary and fantastic results. Okay, so it's like saying that they create, language models create their own grammar in form of what Hewitt and Manning and Clark call latent grammatical structures. Latent grammatical structures because we don't tell language models to do them, to create any structures like this. Okay. And that's the minute.
Sorry.
Okay, no, that's perfect.
I'm the bad.
No. That's what I wanted.
Thank you very much.
You're
Thank
welcome.
you very much. And your question about how do generative artificial intelligence systems do it is for Leo,
Okay.
for Leo Wanner, Wanner E. And please, could you give us an introduction
Okay, something is
to try to understand?
distorted. So I've been asked now to give a short introduction to how generative language models work in 5 minutes. So I think that's mission impossible. No, so but I will try to do my best. Maybe not in 5 minutes, but maybe in 10 minutes. No? So I must say that beyond generative language models, there are many other types of large language models. No? So and generative language model, that's for kind of for generating texts. Yeah. So, but we have classification, we have reasoning, whatever, no? So, and then for generation of texts, no? So, but now let's focus briefly, very briefly, on generative models, no? So, I don't know how much you already know about models in general, no? So, but let's try to, so I hope that I'm not overgeneralizing, no? So I'm still understanding. So let's imagine we want to know from an LLM, so, and well, what does the word armor mean? And we want to receive, or we receive from this model, the answer armor is a defensive covering for the body. This is one of the readings, for example, if we look up in the Longman dictionary, no? So that's one of the senses, no? So the question is, how do we get this from the question to the answer? Okay, so obviously, no? So as kind of very basic, no? So first, no? So what the model does, that's to tokenize our input, our question, no? So and I tokenized this question also using a specific tokenizer, and also this is basically this tokenizer is also used in ChatGPT, for example, one of the last versions of ChatGPT. So what is important to know, no, so that what the modern models do, that's not tokenized word by word, no. So what we have, that's kind of what is called subword tokenization, no, and this just by chance that this tokenizer gave me, no, so here those full words, no, so words, no, so that is what does it mean subword tokenization, no? So that is, as Carlos already pointed out, no, so there are kind of statistical patterns, frequency, no, so the model just looks up what are the most frequent, let's say, sequences of characters in all of the corpora it's looking at. And that just chops off, no? So those segments, and that gets the vocabulary. No, for example, this tokenizer uses then or gets up with the vocabulary of, if I'm not mistaken, but I have it exactly, over 100,000 of tokens. No? So, and the previous version used vocabulary of 50,000 something and so on. No? So that is, we first tokenize, then we get, no? So because we have the vocabulary as such, no? So we don't work with those tokens, we work with token IDs. Yeah? So, and, well, so then Carlos already mentioned this, no? So we kind of embed those tokens, no? So, and this is the input. What does it mean, the embed? And as Carlos also already mentioned, this is kind of, we put each token now in relation to all the tokens in its context, on the one hand, and on the other hand, now, so we also kind of calculate how much this specific, one specific token contributes to the context of the other ones. Yeah? So that is, here we have such a matrix, no? So that is, it's ARMA, and in reality, no? So this is the real embedding, no? So that is embedding, no? So we have here the entire vocabulary here, and we have here the dimensions, no? And already I kind of put it here that we have in ChatGPT approximately. So we have 16,000 something dimensions. That's our length of the vector, and we have a vocabulary of somewhat above 100,000. No, so approximately, because in ChatGPT this is not disclosed. No, okay. No, so and as I already said, the embedding is basically the relation of the token to other tokens and the other way around. So, and we embed the tokens, but we also embed the positions. All the positions, no, so we can have here and in our, let's say, training corpus. No? So in ChatGPT, for example, so we work with the length, the input, the, let's say, maximum input, that's 1,200 to 28 tokens, and we have, that's approximately, so 300, 400 pages of text. This is what the model kind of takes into account when it works with one specific input. Okay, so that is, we embed the position. That is, it's the unique order sensitive vector representation for a specific position. Then we basically add up the embeddings of the tokens and the positions. No, so that's okay. Why doesn't this make sense? No, so we have, for example, here the two sentences: "Knights wear armor, and armor protects knights." No. So that is here, no, so that's in position, armor in position 3. No, so this kind of is a direct object. And in 5 here, so that's subject. That is, the position already gives us some basic surface information. So that is, we combine basically semantic information, distributional semantic information, and let's say already surface information. Okay, so then on top of the token embeddings in general, so we also want to know how in my specific input, the tokens are related to each other. Yeah? So that is how, how contextualized this is. Yeah? So, and here I used another tokenizer, that's the GPT 3.5 tokenizer, and here we see, okay, that's unfortunate because the slides are distorted here. No, so but we see that there are some pop-up. Okay, we don't see anything here. No, so but that is what we are supposed to see. That is how one token contributes to the other token. Basically, in my input. And this is called self-attention. No? So self-attention of the tokens in the input, in my input sequence. So, okay, self-intention, I don't want to go into details how this works, Well, basically, so we have our input, our question, now what does this word arm mean? And we have token embedding, we have positional embedding, we learned about, and then we add this up, and then we get this self-attention layer. No? So I just had on the previous slide. Then we normalize. We don't need to care about here, no? So how this is done. And then we actually start our processing. This is our actual kind of real neural network. This specific type of neural network called feed-forward network, because here we have a fully connected layers, so of neurons. This is my input, and we have two hidden layers, so to speak. And basically, so what at each node, there's basically a mathematical function. And what it does, it takes this number, let's say, we have here, and it basically does this calculation. There are specific functions which are specifically kind of tuned for that. Yeah? So we don't have mathematicians here, so hyperbolic tangent and so on and so on. No? So those specific functions. Okay, also that is, we propagate, let's say, the energy of each neuron, we propagate upwards. Yeah? So, and then we normalize again. No? So this is what we have here. This is what we call transformer decoder block. No? So because our generative language models, they are based on so-called transformers. So, and what we do, well, for example, in ChatGPT, no? So we stack those blocks one on each other. That is, well, for example, now, so we have in ChatGPT, we have basically 120 blocks. That is, so then it's kind of those kind of values are propagated up again and again and again. Yeah? Good. So this is basically what we do with our input, with our question. Yeah? So then we arrive here, so at the final, our 120th block, and then we have our final, let's say, layer, which maps basically the what we got here onto our vocabulary space. Again, no, we are back to the tokens. Yeah? So, and here then, we basically calculate the probability. We apply again a specific function, which calculates the probabilities of each token. So then we say, okay, now so here the highest probability is for, let's say, R. Now, so and this is the first token of our answer. Yeah. So that is the model calculated that the sequence after our question, no, the first token in my answer should be R, because it has the highest probability. So then this token is added to my input. Yeah, that is our question. What does the word arm mean? Question mark, and then arm, and we start the entire game again. No, so then we get arm is, and again, no, and then we kind of token by token we generate our answer. No, so this is why we have generative language models. Okay, so well. The question obviously is, no, so how do we train our, let's say, embeddings, and how do we train those W's, the weights, and so on? So it doesn't come just kind of out of nothing. So what we do, we first kind of initialize this this matrix just randomly. So, and the same with the positional embeddings. And then, what we do is to generate, no, so we know, no, so when we have a specific token, we know which token we want to arrive at. Yeah? So when we calculate here, we map our, let's say, this layer onto probabilities, and we get something we don't want, that is our output doesn't represent the target token. So then we calculate what is the difference, what is the loss between the representation, the target representation and the actual representation value. And then we propagate back. No? So using, again, some specific mathematical functions, we propagate back and tune our, let's say, random values. Yeah? Until we basically, and this kind of goes again and again, until we basically achieve the minimal loss between the target and what we have in our representations, our embedding matrices. And basically the same procedure is applied when we train the model to answer correctly. So only that we apply, or in ChatGPT, let's say, so in other generative models, what they do, they apply additionally other machine learning techniques, like reinforcement learning and etc., causal reasoning, and so on. So I don't want to go into details here. Basically, the procedure is the same. So that is, we have, as Carlos said, also we have massive volumes of text, and we train, applying this rather simple, let's say, architecture, we kind of apply it in order to train our model. So this is basically what generative language models mean. Okay, why do we need? Now the question is, why do we need generative language models? So, and I refer to Carlos now. So to ensure a large scale coverage, so of and high quality of NLP applications. So and this machine translation, so speech recognition, conversational agents, and so on, so on. So before we had language models, large language models, not necessarily generative language models. So we were able to develop, let's say, small to mid-size grammars. And if we, for example, so we kind of, François started this in Stuttgart and then continued at Pompeu Fabra. So we achieved large coverage generation grammar for English, but it took François a couple of years, then his successor another 7 years to achieve this. So a large coverage generation grammar for English. So with the models like this, so obviously we can do it much faster, and maybe also, with better, let's say, a little bit better quality. Yeah. So and what is also important, so we can use, or we should use as linguists, and we'll certainly come to this later. So we should use language models as an instrument in order to discover, let's say, linguistic knowledge. It's there. Yeah. So, but we need to look at the models, to analyze them, and kind of to be able to better describe linguistic phenomena, which are kind of hidden. And then, obviously, compile large-scale, for example, so we're here at the linguistic lexical, let's say, conference, lexical resources, dictionaries. So I'm sure that there will be large coverage specific dictionaries for specific domains and specific topics, for example, collocation dictionaries, generated by or compiled by language models. So, and I mean, if we use, I'm very sure that all of you already use, for example, ChatGPT, DeepSeek, or whatever, and experiment with prompt engineering. I think that's a nice way to get into this topic. So just kind of try, so what we can get from a model. So just fine-tuning the queries. Okay, and yeah, so I asked.
This is for the last part.
This is what things about the future. Well, that's a kind of a generative language model itself, no? So what it thinks, no? So how linguists could kind of help it, no, to advance. So okay. So that's the first part or the second part? I'm not sure. So yeah, okay. No, so I'm finished. Sorry, it took me more than 5 minutes. Yeah. Okay.
Thank you very much. It was difficult to introduce the concept.
So, so let's move to the second part of this roundtable, and in this second part we will focus on the lexical knowledge. We will explore in depth the lexical knowledge in these large language models. And the question here goes to Professor Lareau. As we have seen that the linguistic knowledge in the generative large language models is encoded in a different way. So the question that we would like to discuss here, what kind of knowledge do they really have in terms of lexical knowledge? I mean, what kind of knowledge do these large language models have in terms of lexical knowledge? So the floor is yours. Sorry.
Okay. Well, first I'm going to focus on lexical knowledge, as you already mentioned. Of course, we could ask the question about syntax or morphology or other parts of the language knowledge in general, but this is a conference focused on lexical knowledge, well, the lexicon. So it's not so obvious to answer this question because there's no fixed way of evaluating these things. We're developing ways of evaluating these models. I would say that currently a lot of the evaluation of language models that is currently being done is not at all focused on the language. A lot of efforts go into testing the languages for their factuality, their conciseness, their ability to answer questions, to perform tasks, things like that. Obviously, this is because this is the utility of these models. We don't just use them as models anymore. We use them as assistants. We want them to do things for us. We want them to answer our questions, to perform certain tasks for us. So a lot of computer scientists work on this kind of evaluation. But this is of no interest at all for linguists. The fact that a language model would say that Madrid is the capital of Poland, for example, means nothing for a linguist. It's linguistically perfectly correct. It's just factually wrong. Humans do that all the time. You and me and everybody every day says something that is wrong, that's factually wrong. And you might know it's wrong, or you might not know it's wrong, but you say wrong things all the time. But you say it in good language. And actually, you could say that politicians who are really good with language, or they speak very good language, they often say things that are wrong. So factuality and language skills are completely different things. So how do we bring back the evaluation to focus again on the language itself rather than factuality or knowledge? In terms of lexical knowledge, we have to first figure out what is lexical knowledge. What do you expect a machine to know about your lexicon? What is there to know about the lexicon? There are a few low-lying fruits here to answer this question. Open the most basic dictionary that you can buy for €2 at the shop. Each word you will have information about its part of speech or syntactic category. Is it a verb, a noun, an adjective? And some kind of basic definition which may be more or less refined. So these are the two most basic parts of lexical knowledge that you would expect anyone or any language model to know about words. But this is not the most difficult part for these languages to acquire. because likely it has seen this explicitly in its training data. In the training data, there is a lot of text from all kinds of things. That includes all of the Wiktionary in every language and every dictionary available publicly online. And for some of the models, I would suspect also several dictionaries that are not publicly available, that for some kinds of reasons that are kind of legally, it ended up somehow in the training data. So these systems have seen definitions of words, have seen next to the word that this is a noun, this is a verb, and so on. So asking a model, what is the definition of that word, what is the part of speech of that word, is basically the same as asking what is the capital of France. It's a factuality question. You've seen this in your training data. Please answer this as you've seen in your training data because it's explicitly in the data. But that's just the tip of the iceberg of lexical knowledge. There is some kind of occult part of lexical knowledge, which is the relations between the words. This is never explicitly stated anywhere. Most likely in the training data there is very little about this. There are probably not a lot of dictionaries that will explicitly encode a lot of lexical relations, except perhaps synonymy or antonymy, which might be more recurrent. So that's what we've been trying to do in our lab. We try to see if by just being exposed to large amounts of text, these systems are able to extrapolate from that and generalize relations between words. So what do I mean by that? I mean that, for example, you might see in your training data that you can say, to build this house took a year, or it took a year to build this house, or the construction of this house took a year. And you should infer from that that construction and build mean basically the same thing. It's just one is the nominalization of the other, or the verbalization of the other, which way you see it. It's not explicitly in the text. It's not explicitly usually in any of the commercial dictionaries or the ones that they're likely to be exposed to in their training data. But we as speakers know this somehow implicitly, and as linguists we know it explicitly, and we try to teach it also in linguistics courses. So what we're trying to do is to see if these language models are able to generalize from their training data to acquire this kind of relations. So how do we do this? There are a few ways you can probe a language model. One is one you've probably tried at home. You've likely interacted with a chatbot at some point. You just ask the machine, what is the normalization of build? And see if it says construction. So this interactive session is one way of prompting, not prompting, but probing the knowledge of a language model. Another way is a task that's called unmasking. So you show a sentence with one word or a certain number of words missing, with a special token that you put that explicitly says, I've masked a word here, and let the model unmask this word. So you could say, if you want to see if a language model knows about certain idioms, I could say, this guy just gave me the blank shoulder. And if you've paid attention to Paulier's talk this morning, you should know that the blank here should be replaced by cold. And the system, I would expect it to return cold as the answer. A third way of interacting with these systems is to go play directly with the numbers, extract the vectors that Leo just showed you, and see how close it is to other vectors. And you would expect words with similar distribution to have similar vectors. So we can explore different ways of evaluating the models using these three methods of probing the system. So we've tried at least the first two in our lab. So for the case of idioms in particular, we tried to use a large database of idioms. So we used the lexical network of Polgar and his minions. We have a list of idioms. We have a list of lexemes that are not part of idioms, and some sentences in which these lexical units appear. And then we take these sentences and mask some words, and sometimes the words are in a free expression, sometimes the words are part of an idiom. And we see how easy it is for the model to guess the word. You would expect that if the word was part of an idiom, the model would be more likely to output the correct word, because there's a full idiom around it to guide it. If I say, the example I just gave you, it's fairly easy to guess that cold was missing. If I say, I saw a blank this morning on the street, what goes here? You don't know. You don't know what I saw, and it's not part of an idiom, so there's no prior knowledge that you can activate. And indeed, in our experiments, this is very clear. The system guesses idioms, words that are parts of idioms, much more easily than free words. Now, idioms are not all equal. There are different kinds of idioms. They can be more or less opaque semantically. To give the cold shoulder, if you don't know this expression, you're never going to guess what it means. Whereas, I don't have an example in English, but in French, that little animal that lives in the sea, that's the shape of a star, we call it a star of sea, literally. Okay, étoile de mer. It's a starfish. If you've never heard étoile de mer before, but you know these three words separately, you will guess which animal I'm talking about, because it's very compositional semantically. All that's missing is animal, basically. And so we wanted to compare. We had three different degrees of compositionality for idioms, and we want to see, is it easier for a system to guess an idiom where the word missing is compositional or non-compositional? What we observed is that there was no difference, basically. The system makes absolutely no difference between a fully opaque idiom and an almost fully compositional idiom. And that's a very disappointing result at first for us. We were like, oh, no, damn it, it doesn't give the result we were expecting. But maybe it means something. We have to keep in mind that maybe the theory is wrong, or maybe what we are measuring with these models is not exactly what we expect to be measuring. We came to the conclusion that actually these systems are not that much sensitive to meaning. They don't really care about meaning. They care about distribution a lot. Only distribution is what guides the construction of a vector, an embedding. And so whether it is compositional or non-compositional is not relevant to this model. What is relevant is it constrained or not in its construction? And what is an idiom is it's always constrained. Otherwise, it's not an idiom. By definition, an idiom is constrained. And so that's why these models are not seeing any difference in terms of compositional or non-compositional idioms. So that points to something that is very important to highlight. The lexical constraint of idioms is actually more important than semantical constraint, and it's not discussed as much in the theory. Now, I said there are three different ways you can probe the system. Another way is to just ask a question and see what it's going to answer. So we tried that too. This time with collocations. So what we did is we did some prompt engineering on how to ask a system about a lexical function and see if it knows about a certain lexical function. So again, we pumped the data from Lexical Network of French, And we took the most common lexical functions, the ones for which we had enough data to conduct tests. And we have a kind of description of each lexical function. So we have something like magn is a lexical function that encodes a relation of intensification. For example, here are some examples of magn. And then you have 10 good examples of a pair of a base with its collocate that is a magn. And here are 10 counter-examples. Then you would have examples of other collocations, but that are close to magn, but not magn. You would have like lexical functions like bon, which encodes the positive appreciation of something, or other modifiers that might be confounded with magn. And now I'm going to ask you some questions. I will show you a base, and you will return the magn of this base. And I return only one word. And yeah, that's one problem with these systems. They tend to be verbose. They don't just answer with one word. And so then you ask for a different base, and you see how good it is at coming up with the right answer. Turns out they do really badly on these tests. Now, we don't care if they do good or wrong because we didn't make these tests, these models. And we're trying to create a benchmark that we want to be able to use for different models, and you can compare the lexical knowledge of these models. But it turns out that also when we tried these tests on ourselves, I would be embarrassed to report my own results. It was actually pretty low. And so there is maybe something poorly designed in the prompting. We have to refine it. We have to take into account polysemy, for example. You cannot just say what is the magn of, I don't know, feeling, or I don't know, any word, because the system or the human reading the question might think of the base in a different meaning and give the magn of that meaning, and it's not the right meaning associated with the base that you had in mind in the question. So we have to include in the question more information about the base, like I'm talking about this specific sense of this word. Here are some contexts that will help you figure out which sense I'm talking about, and so on. Anyway, so we're still working on this. I don't have the final results of these experiments, but clearly these systems are not particularly good at extrapolating these relations. And although the results are preliminary, one thing that is very clear for now is that they rely heavily on morphology, or so-called morphology. That is, it will be a lot more difficult for the system to see that the nominalization of build is construction than it would be to see that the relation between sleep, the verb, and sleep, the noun, or constitute and constitution, things like that. Things that are morphologically related will be a lot easier for the system. And sometimes it would come up with an answer that seems to be really contaminated with similarity of forms. And it's not really morphological per se. I think this is a lot because of a problem of tokenization. So Leo already said that tokenization is not necessarily word by word. Indeed, it is very often subword by subword. And the subword tokens, it really depends on the model, but for the models that don't have like hundreds of thousands of different tokens, the mechanism will be that you will have some tokens that are likely to be morphemes, like ing in English, the ing at the end of the word likely will be a token. But sometimes a token will be, if you take a word like emotion, for example, you might have emotion as tokenization, which is absolutely horrible from a morphological point of view. It means nothing. It's nonsense. And so it might see the same E and the same mo in emoji, for example, which in this case might make a little bit of sense, but also maybe in other words that might look similar but are not really similar, but just it turns out that you have the same E and the same mo in this word. So I think that's why it's a lot contaminated by the morphology. It's just a kind of similarity of form. I think that's the time I had, right? Yeah, okay, sorry.
Yes.
So first question, what can the role of the linguists in relation to AI? I think it's to evaluate them, and we're better suited than computer scientists to test the linguistic ability of language models, and we have to reach to our colleagues in didactics. They've been doing this all along, evaluating students' ability of linguistic abilities. But also I would like to flip the question, what does AI do for linguistics? And we have to learn to use it as a tool. This is the best corpus you've ever seen in your life. It's better than any other corpus. It's a huge distilled corpus, and it's sort of an infinite corpus because it can create new sentences on the fly. So you can see it as a native speaker who speaks the language perfectly and who will never get tired of your questions. So that's a dream for a linguist. Now, the skills I would look for in a linguist who would like to, I don't know, join my team or something like that, the ability to code in Python so that they can interact programmatically with these language models. It's not complicated. In my experience, in a few months, people have zero experience in programming, reach a level where they can do stuff. That's one. Basic understanding of linear algebra, because you're manipulating matrices, and you have to know what it is and how to do some basic operations on them. It takes really a few days to learn. Just the basics, not the full thing, but just the basics. And statistics, because the results you get can be misleading. In the experiment we did with the idioms, we tried 3 different levels of idiomasticity, of compositionality. At first, when we saw the graphs, we were like, yeah, it works. There's a tiny difference between the 3. Then we ran the statistical test, and no, there's absolutely no significance here. You have to be able to perform these tests, otherwise you will come to wrong conclusions.
One question, so the boss says one question.
Carlos, could you please repeat this?
Piantadossi, pronounced in Spanish. It's 2023, and it's online.
Thank you.
And it's I don't remember the title.
It's okay.
But it's online, and you will find it very fast.
Okay, so I think there have been a lot of issues raised that could be discussed later in the coffee break, but let us wrap up this interesting session today. So we just a summary, a brief, with the main points and the main findings that we tackled today. First of all, we started from a historical point of view, discussing where we come from since the conceptual frameworks and the FrameNet and the frames to introduce meaning to the computers until we reach to the embeddings and to the encoders and decoders and the matrices. So this was the first part, and in the second part we discussed in more in depth the lexical knowledge in the large language models, and if there is really a sort of lexical knowledge or not explicit, and we saw how are the different experiments to evaluate this knowledge and to what extent how the large language models encode this information about collocations or about certain idioms. And finally, in the last part, we had the opinion of our three guests today about the role of the linguists, and I think the main message that the takeaway message from this final part, that the linguists today should see the large language models as an instrument and not as competitors, and also they have to learn more of this distributional, the coding in Python, statistics, and algebra, to be aware of what results are they giving to us and how to improve and how can we interpret actually these results. So I hope I managed to wrap up all the points discussed, and of course thank you again for your interesting discussion and contributions, and thank you for the audience for your time. Thank you.
Toda la tarde.
Qué bueno, cómo me ha gustado tu experimento. ¿Sabes lo que estás haciendo ahora? Tenías una tesis en la tesis, ¿no? Que tenías.
No, tengo un estudiante.
Ajá. Es un laboratorio, es verdad. Es un laboratorio para...
How's the name? Piantatosi, you said?
Piantatosi.
Piantatosi, okay.
Vamos a borrar, ¿quieres que borre?
Can you write it down?
Yeah, of course. Faltaba más. Yeah.
Okay, this one, okay. Good. Okay, thank you.
You're welcome. He's tough on linguistics. No. I think the name is Italian. He's actually American.
But
He's, yeah.
He's from Berkeley.
Berkeley.
psychology?
I think he's from the Department of Psychology.
Okay.
But he knows a lot about linguistics and artificial intelligence also. So it's very broad view. Yeah. So it's you're welcome.
La verdad es que sí estamos en contra de eso.
Bueno, gracias.
De verdad es apasionante.
No sé si ha quedado muy claro porque yo estaba aquí un poco patinando.
No,
Bueno,
hombre,
vamos
es que
a cerrar
todo esto tan difícil de entender, pero por lo menos...
¿Sí? ¿Se ha quedado claro?
Sí, porque yo no tenía ni idea de por dónde iban los tiros, es que tampoco he trabajado nada de esto. Y entonces, pues ya he visto que no era nada de lo que yo me imaginaba, que vamos, que lleva su vida, la inteligencia artificial, su vida matemática.
Tiene su vida, tiene vida propia.
Tiene vida propia. Pero es un poco lo que pasa a la gente, ¿no? Porque cuando aprendemos, un niño no sabe nada de gramática. Oye algo que se repite y se va a quedar con construcciones, cosas que entonces de alguna forma es lo mismo, ¿no? Digo yo, no sé.
Habría que verlo. Habría que consultar a los que saben para... No, we were talking about... Estábamos hablando del tema este de si se hacen estructuras internas dentro del modelo.
Bueno, hay que definirlo como qué quiere decir hacer estructuras. Si hablamos de estructuras sintácticas, digamos, de relaciones de dependencias, eso sí, ¿no? Se puede como en una capa
por ninguna parte, pero bueno.
Relaciones de dependencia entre, digamos, los tokens, ¿no?
Sí.
Entonces, desde allí, obviamente, no podemos construir, ¿no?, un árbol. Sí, y
Gracias, Chapo.
de la misma manera, diferente, pero también hay trabajos que lo hacen en el nivel discursivo, ¿no? Entonces, como un árbol de, por ejemplo, de Rhetoric Structure Theory, ¿no? O sea, es un árbol discursivo, ¿no? También, ¿no? Podemos en el nivel un poco más abstracto. Sí.
¿Ah, sí?
Sí.
Pues si se puede en el nivel, a este nivel, se puede hacer un frame.
Sí, bueno, a ver, ¿no? Si tengo que pensar si ya no hay trabajos con FrameNet.
Sí, he visto, pero no trabajos de anotación.
Bueno, sí.
Uno de los objetivos, perdona, uno de los objetivos es poder anotar, que es un trabajo muy laborioso, poder anotar automáticamente.
Si puedes, ¿no? Si pasas al modelo, ¿no? Una frase, un texto, que te analice en términos de semántica de frames, y te devuelve el resultado, entonces tienes, ¿no? La anotación, puedes volverme y anotarlo.
Claro, pero yo me gustaría probarlo, no he tenido ocasión, porque normalmente todas las construcciones que se anotan son distintas entre sí. Entonces, nunca hay una regularidad absoluta.
Sí, bueno, eso es el problema. Bueno, depende de la estabilidad, ¿no? Un poco, ¿no? Sí, eso es